Hello, it's Keith here, and this is lesson 54 of the platform-specific series of my 68000 assembly programming tutorials. Nearly got the title wrong there. Now we're looking at the NeoGeo again today, and we're looking at MinTile again, my simple tilemap example. What we're doing this time though is we're using the hardware sprites. Now last time we used the fixed layer. Fixed layer is not really designed for this kind of thing. What you're supposed to do, what we've done here, is you're supposed to connect lots of hardware sprites together into a virtual tilemap and then use that as for your graphics. So what we've got here is another example. We've got the scrolling background again, which is done with the a combined giant block of sprites, and then we've got our characters moving around the screen, which are made up of separate sprites. Now you'll notice the background graphics look very small and don't look the same as last time, and there's a good reason for that. Now I'm reusing the old graphics that I used for my YQuest game, and with YQuest the graphics were supposed to be 8 by 8 pixels, and so I simply filled the rest of the area with black pixels to make them transparent. That worked fine for YQuest, but for this example I'm making the 16 by 16 sprites 8 by 8 by scaling them down by 50%. And so really what I need is graphics that are double-sized, which is what I've done for the Chibico character. For compatibility, even though the sprites on the NeoGeo are based around 16 by 16 pixels, I'm scaling them all by 50% so that everything works the same as the other systems. So my source data isn't really right, which is why we've got these weird tiny little blobby graphics for the background tiles. If I re-edited the tiles and re-exported them, they'd work fine. But I didn't want to add more kludge to the XML file for a simple example. So there we go. So let's go over to our code and let's take a look at what we've got. Okay, so once again, I'm going to assume you've seen the previous example for MinTile. I'm going to still cover most of the content, but if you're interested in MinTile and this NeoGeo example, please see the previous example as well, using the fixed layer. That was lesson P53. Anyway, so we need to define sprite data because, of course, the sprite data is different to the data for the fixed layer. So we need pairs of files for the opposite bytes in memory. So we've got 2 for our MinTile Chibico example here, and that's different in format to the Chibico bitmap, so that's separate there. And we are reusing our YQuest data up here, which is why it looks wrong. So that's our data that we've included in our XML file. Now, how do we actually get things to the screen? Well, let's go back to our our web page view, and let's just see the description so that we can briefly discuss all of the concepts and the capabilities of the NeoGeo sprites and the VRAM memory addresses that actually do the job. Okay, so the way the sprites actually work is a little bit odd. Each sprite is obviously a 16 by 16 pixel object somewhere on the screen, but we can actually chain multiple tiles into a single sprite. So a single sprite is always 16 pixels wide, but it can be actually much taller as a combination of these extra tiles. And so basically one sprite can have up to 32 tiles vertically chained onto it. Now we can then connect neighboring sprites to each other horizontally as well. So we go vertically with the tiles and horizontally with neighboring sprites. And so if we wanted a 32 by 32 sprite object, we would actually only use 32 sprites for the 32 columns, because the tiles within those sprites would actually do the job going down the screen. So let's take a look at the memory addresses that the hardware sprites actually use. So let's take a look at a sample example of sprite 1 and the memory addresses that would build up the various options of sprite 1. Now each sprite can use multiple tiles to build a taller vertical sprite, and so each of these sprites has various tile addresses, and these start based around the memory address quadruple 0. And so this single sprite can have up to 32 tiles, and these will take VRAM addresses like 40, 42 and so on, and each of these addresses actually takes a 16-bit value, and the 16-bit value in those addresses would be just the tile number. Now there's 2 bytes here, but that's not why we go from 40 to 42, because the memory address 0040 actually takes a 16-bit value. The memory address 0041 actually takes other data relating to those same tiles of sprite 1, and that's the palette, some more bits of the tile number, and animation options. We can actually automatically animate the sprites, the tile pattern, sorry, and we have X and Y flip, a vertical and horizontal flip there, which will be very useful to us. So those are the memory addresses related to the vertically chainable tiles. So that's going down the screen. Now beyond that we have other memory addresses being used. Memory address 8000 and onwards 8200 and onwards, and 8400 and onwards, and these take a single address with a 16-bit value in it for each of our actual sprites, so no longer related to the tiles of the sprites, the actual sprites themselves. So one of these is the shrink option, and this changes the scale of the sprite. Now that sample value I believe will be full size, but we're actually going to scale by 50% because the sprites by default are 16 by 16 pixels, but I want them to be 8 by 8 to maintain compatibility with the other versions. So that is what we're going to use there. We've then got the Y position at 8200 and onwards. So we've got our bits for the Y coordinate. We've got the C option, which is the chain option. And this is how we connect multiple neighboring, numerically neighboring sprites into a big tile map. So sprite 1 can be chained to sprite 2, can be chained to sprite 3, can be chained to sprite 4. We can only chain to the following numbered sprite, but then they all move as a single object. We could, of course, move them all separately, but that would be more work. So by chaining them, the X and Y coordinates all chain together. Okay. We then have the tile count, which is how we define how tall this entry is. So we can set that and define our tile count as we want. So our background will be lots of tiles, but our sprites are all made up of 8 by 8 individual objects. Again, not the best way of doing things, but to maintain compatibility with the other systems. If you were writing only a NeoGeo game, you wouldn't want to do that. You'd want to create your graphics at full resolution with as many tiles as convenient. But as I say, these tutorials are all about multi-platform, maintaining compatibility across a lot of systems. And then finally at 8400 and onwards, we have our X coordinate using the same bits as the Y coordinate, and the bottom bits don't do anything there. Okay, so that's what we're going to have to actually deal with in our code. Okay, as I said before, we're not going to discuss the stuff relating to joysticks and moving the object, calculating the coordinates, because we've done all that before in the simple series. We're also not going to discuss the multi-platform code. There is a whole tutorial series on MinTile which discusses the multi-platform code, and there's videos matching it, so please take a look at that. What we are going to start with though is actually building our fake tile map. As I say, it's not a tile map, it's actually a set of sprites. So that's what we're going to do. Okay, so the first thing we're doing here is we're selecting the memory address *0 in D6 here. That is going to be our VRAM destination. So we're basically going to start building our tiles here. We're going to start with sprite 0, not sprite 1. So we're starting at a different memory address here. And then basically what we're going to do is we're going to work through these and build all of our sprites. Now our screen is going to be 32 tiles wide and it's going to be 24 tiles tall. That's 256 by 192. So that's we're loading our counters here. These are going to be used with dbra commands for our loops. Okay. Now the first thing we're going to do is the special top left corner anchor sprite. As I say, we can use the chain option to combine the sprites that make up the columns into one single object, and the various tiles going down are automatically part of the first object anyway. So this anchor sprite is basically moving this would move the entire tile map. Okay, so the first thing we're going to do is we're going to set the data and memory address 8000 onwards, and so we want the shrink options here. And we're loading those in. We're using 7.7f here, which is effectively a 8 by 8 scaling, so 50% size, and that's going to simulate the tile size that we want. Okay, so we're going to load that VRAM address, and then we're sending our value for the shrink there. Next, what we're doing is we're moving to memory address 8200 here, and we're going to basically define our Y position and also set our size. Now what we're going to do here is we're going to set the Y position at F0, which is the correct position for the sprites. I believe they go up the screen if my memory serves me correct. A little bit strange, but that's, yeah, they go up the screen, so a little bit odd. There's a calculation here that you can use to convert your coordinates if you need to, but that's the coordinate we need for the top left of the screen there. And we're setting the number of tiles is 33. This is a special looping option, which is what we need for a sprite that fills the entire screen basically. So that's why we're selecting that. We're then selecting our X position, which is from the left, so a bit more sensible there so in some ways. So we're selecting the 8400 onwards value here, and we're setting our X position here. Okay, and then what we're doing is we're jumping back to the position for the shrink for next time. Now what we've got next is our sprite loop. Now this is going to be run for each of the columns because we need a different sprite for each column, but within each sprite we need to select multiple tiles, and these are for going down the screen. Okay, so what we're going to do is we're going to specify our tile address first here. So we're specifying the memory address 0 and onwards here. Now we're using D6 for this purpose here. We loaded D6 up here. And so this is relating to this tile. So what we're going to do first is we're going to load our tile number. We're loading a generic tile number here. They will actually be all set later on by our code, our do strip routine. We're then moving to our palette and setting our palette to palette 1 here. We're then going to basically repeat. So we've defined basically our first tile here. And we then need to do this for all of the tiles going down the screen to build one entire column there. So that's what we're doing here. We're repeating until we've done our entire column. Once we've done our column, what we're going to do is we're going to define the other attributes for this sprite. So what we're doing next is we're basically updating D6 to point to the tile data for the next sprite. So we're jumping effectively from 4.0 to 8.0 and so on here. That's basically what we're going to do there to move to sprite 2's tile data here. That's what this calculation is doing here, and we're moving to the next sprite in D7 as well, which is far easier to do really. Now we defined our anchor sprite up here, but the other sprites don't need the X and Y coordinate because they are all chained to that anchor sprite. So we've got the settings here for the remaining sprites here, so we are loading them here. We're loading our various settings here, but as I say, the Y pos won't actually do anything, and neither will the X pos here. So these, apart from that, these are basically the same kind of concept and certainly the same data as the anchor sprite up here, but as I say, the coordinates, because of the chaining, don't actually have any effect. And then we're just repeating until we've built up all of our sprites, and that is how we basically are chaining 32 sprites together to build up our background tile map. Now if you wanted multiple layers, then you would actually do this multiple times. So you would use 0 to 31 for one layer and 32 to 63 and so on. So you could build up a much larger tile map in that way. And I believe because of although the NeoGeo has an awful lot of potential sprites, there is a limit to how many can be on a single X line because of the way the hardware works. I think there's a physical limit of 4 layers on the NeoGeo. You would basically run out of sprites at that point. And so that's how we're able to build this tile map here that we're using for the rest of our code. So that's just built the initial state of the tile map. Now what we're going to do next is we're actually going to have all of the same code as we had before. So we've got our do strip routine as before, and this is going to basically draw to the tile map. So our screen base, actually this value is now no longer used. What we're going to have to do now is we're going to calculate our VRAM destinations based on the X and Y coordinate. So we've got our do strip routine here, and what this is going to do is it's going to basically calculate the correct tile within the sprites that we've used for the tile map, and it's going to alter the pattern data for that tile to show the graphic that we want to the screen. So we've got our code here as before. We're loading in our tile number here. We're checking if we need to clear it because the background tile map is a cache, as I said before, so we're clearing it in that case. We're then adding A5, which is the pattern offset for this tile pattern data. We use a different set of tiles for the tile map for the background as the sprites, because we only use 1 byte per tile number, but by using different source data we can have more than 256 tiles on the screen, so that's a benefit there. And then what we're going to do here is we're basically taking the X coordinate here and we're effectively multiplying it by 64. Now the reason we're doing this is to effectively calculate the tile address of the column that we actually want to change, because we're going to change the tile number for one of the sprite tiles on the screen, and so we're multiplying the X position to calculate that. What we're then doing is we're taking the Y position and effectively multiplying it by 2 to select the offset, because remember the tiles going down the screen within the sprites, there are 2 memory addresses for each of these settings here, so that's why we're multiplying that by 2 and the XPOS by 64 to select the appropriate tile and to select this entry for that tile. Okay, now what we're going to do next is we're going to select that VRAM destination there, so we're just writing that to 3C000 there, selects the VRAM destination, and then what we're going to do next is simply write the tile number that we've calculated, basically the source tile number plus A5 here, into that VRAM destination, and that selects the tile number that we actually want to show to the screen. And so that's how we've done that. That will draw our tile to the screen. Now this do strip routine is just for the background tile map. We sort of could use it for everything, but being as we're using hardware sprites now, we want the smooth per pixel movement for our characters, and if we used the background tile map, we'd still be used we'd still be limited to that 8x8 grid, which wouldn't be very good. So what we've got is we've got an alternate version called doStrip Sprite. Now this will actually use extra hardware sprites and build up another miniature tile map at any XY coordinate that we need to draw this sprite to the screen. Now we've got a parameter here called hSpriteNumber. Now this is actually the next free hardware sprite. Now we've used the first 32, 0 to 31, for our background tile map, and so 32 is the first hardware sprite that's available, and so we're writing that here, and that will initialize that value, and then every time we draw a sprite to the screen it will use a following hardware sprite, and that's how we're going to build our object up. So we're loading our hardware sprite number here for the next free hardware sprite to draw this part of the character to the screen, and we're going to build the character up in 8x8 pixel blocks for compatibility. As I say, really we'd want to work in 16x16 pixel blocks, but that wouldn't be compatible with the other systems. So we're doing that there, and we're taking the sprite number and we're multiplying by 64 because we want to select the correct part of this here, and this part here is in 64 address increments each time for each hardware sprite. So that's why we're multiplying this part by 64 here, and this is going to allow us to select our tile number. And then what we're doing here is we're writing our tile number, adding a 5 to our selected tile number and writing that into the VRAM write port there. So we've selected our VRAM destination and then written our value to it. So we've selected our tile now. We're then moving to the next memory address, which is this palette data here, so the matching palette data, and we're just going to basically write the value 100 there to select palette 1. We're then going to set the shrink option here, and we're going to again set 77F here. We're then going to move to memory address 8000 onwards, offset by hardware sprite number here, because this is the shrink data. We're then going to write our 77F here, which is a 50% scale, and that's to give us 8x8 pixel tiles to match the other systems. We're then going to add 200 here. This is selecting our Y position here. We are taking the starting value of 241 here, and then we're subtracting our Y position here, and we're doing some bit shifting here. As I say, the X and Y position, as I said before, are in logical units, pairs of pixels, and so we're converting this into a pixel coordinate here. And then we're basically going to write this to the screen here, and we're then going to write this into VRAM here. Our height in tiles is just one tile. As I say, we're not using all of the capabilities of the NeoGeo because it wouldn't be compatible with the other systems, not easily anyway. So we're not going to use that. We're then moving to the X position and again calculating our X coordinate. So we've written all of the parts for this hardware sprite. We've written the tile number, the tile palette, we've then jumped to the 8000 range, and we've written the shrink, we've written the Y position, and then finally we've written the X position. So we've now done everything for this one 8x8 pixel tile of this sprite object, because as I say, this Chibi-Ko character here is multiple 8x8 pixel sprites on all systems. So that's what we've done there, and we're just moving to the next hardware sprite there. And we then just repeat until we've done the entire strip. The sprite is built up of individual strips going from left to right in all cases. That's how we draw the unflipped character. What about if we're X-flipped? Well, the NeoGeo's got the power for us, so we have a nice easy job this time. So the only difference really in this code here is we move from right to left in the source tile map. We still draw from left to right onto the screen. The only change here, because of the hardware capabilities, is we set the H bit, the horizontal flip bit of the palette entry. So the top byte is the palette, the bottom byte is partially a tile number and a vertical and a horizontal flip. So all we're doing is we're setting the horizontal flip here, and that X flips the data for us. Much easier than having to provide X flipped data, and that's really all there is to it. Now, one final thing we need to do after we've drawn our hardware sprites to the screen is we need to make sure any sprites that were used before but are no longer needed are actually cleared. And so what we're doing here is just quickly, after we've drawn our sprites, is we are going through all of the remaining sprites that haven't been used, and we're writing their X coordinates all to 0 here. So that's what we're doing here. X coordinate 0 is off the screen, so that's effectively hiding them. Now, if I remove this line here, this finished sprites routine here, and then I run the examples again, it will initially look like it's working just fine, and it indeed will be. But then once we actually start using it, we'll notice some glitches. So if we just get there, here we go. So everything looks fine at the moment, but oh, you noticed already the feet disappeared. And if I start going off the screen, you'll notice there's a trail of weird objects, and those are the hardware sprites that were no longer needed but are now on the screen. And so once we draw the graphics to the screen, we check if there's any leftover sprites that aren't needed, and we have to turn them off basically, which is what that code does. So there we go. NeoGeo sprites are extremely powerful. They're just a little bit hard to use because of, you've got a lot of settings to change, and you've got to track which hardware sprites are in use. And as I say, if you're porting a game from other systems, the question always comes up is how much work do you want to do to get this game looking as good as it can do on this system? Are you willing to completely rewrite your graphics routines? Are you, when you're designing your game, do you design for the least capable system, or the most, or somewhere in between? Because whatever you do, you're going to start struggling to satisfy all of the capabilities of your systems, unless you spend an awful lot of time writing the games. I mean, obviously you could completely rewrite your game from the ground up for every system, but these days there isn't really any commercial market for any of these systems, and so you're likely to be doing this as a hobby. And I don't know about you, but I simply don't have the time to be considering doing that. So I tend to make compromises and make the systems work in similar ways, which is what this tutorial series is all about. Anyway, I hope you've enjoyed what you've seen today. As I always say, go to the website, download the source code, the Rust scripts, use them in anything you want. If you manage to use them commercially, go ahead. I don't quite see how you can, but go ahead and do that. Anyway, thanks for watching today, and goodbye.